Dao from University of Kansas in Lawrence. Hai Long graduated from Michigan in 2006 under supervision of Professor Melvin Hochster. His talk is between two of his talks. He writes, I read his homepage today, that in the days at Michigan, he wanted to solve all the homological conjectures. And he once thought of switching to economics, since he was deeply thinking that it was far easier to solve the world's poverty problem than Sayre's positivity conjecture. And I'm glad to inform him that Professor Hochster will actually be discussing the positivity conjecture next week. Professor Hochster gave his first talk last time, but the real application he will give next time. So problem is still open. And but let me tell you that Long is a very versatile writer in computative algebra. He works on many topics, and it's a pleasure to talk to him. Today he will speak about reflexive modules over curved singularities. And now I invite him to present his talk.
All right. Well, thank you very much to Professor Verma for the kind introduction. First of all, can you all hear me and see the screen?
Yes, it is clear.
Okay, thanks. And yeah, so I actually gave up very easily on the homological conjectures. It was too hard, and fortunately, I think commutative algebra is full of interesting questions that suitable for your level, whoever you are. And so so here we are, and I've been enjoying it ever since, thinking about questions that I can say something about. And actually today it's an honor to talk to take part in this seminar, because India has such a great tradition in commutative algebra, and of course we all know that. And in particular, this is joint work with two graduate students from India. Sharashish Maitra from University of Virginia, he's a student of Craig Unicky, and Prashant Sridhar, who's a student at KU. He's actually a student of Denkas. In fact, this is my first Zoom paper. So via Zoom, we initiated and work on this project entirely during the pandemic. So so let's start. Let R be a Noetherian commutative ring and M a finally generated module. And M star will denote the module of homomorphism from M to R. And we all know that there's a natural map phi from M to M double star. So we just take an element of A of M to the map that send a map, a map from M star F to F of A, right? So that give me a map from M star to R. And so it's give us a map from M to M double star, and M is called reflexive if phi is an isomorphism. So this is, of course, reflexivity is a fundamental concept. I don't know, I'm not sure who's the first one who study it, but at least it was studied in a paper by Diodone in 1958. And I think Hyman Bass in a paper in 1960 called this concept reflexive, right? Because it's called M reflexive if phi is an isomorphism. And it certainly appeared in Bourbaki algebra book. But I'm not sure if Bass is the first one who called it reflexive. Anyhow, reflexive modules are a fundamental concept in both commutative algebra and algebraic geometry, and I think in some other areas as well. They also use the same name. And I think we are familiar with this. However, as I mentioned earlier, commutative algebra is full of surprising questions. If you think a bit about even familiar concept, you realize that that we don't understand them as well as we think. And so the goal of this talk is to try to study and understand reflexive modules beyond the classical knowledge. I will next explain what is classically known about these objects. So let ref R denote the set of the category of finite generated reflexive modules over R. And to understand the reflexivity, you can localize or complete, or in fact, the definition, that this natural map being an isomorphism work very well with flat extension. So you can reduce the problems to the local case, and you can even complete if you like. The second remark is that the obvious reflexive modules are free modules, right? You can check. In fact, I think that was the original motivation, is to extend the duality theory of vector space over field to module over rings. And so the free modules are reflexive. And if R satisfy set condition S2, maybe let me write it down here. So share condition is 2 for module in this talk would mean that the depth of MP is at least so locally the depth is at least the minimum of 2 and the dimension of the local ring. So it's say if I is S2, which is a fairly mild condition, for example, all Cohen-Macaulay rings and all maximal Cohen-Macaulay modules over them are S2. Then M is reflexive if and only if is S2 and is reflexive in codimension 1. Right, so the statement down here again say that M is reflexive if and only if is S2 and is reflexive locally at all prim of height 1. Assume that R is S2. You can say a bit more general, but for this talk, I will mainly use this. So that says that really to understand reflexivity, you need to understand the height 1 case. So locally, when you localize at height 1 prim, you want to show that M is reflexive there. Okay, so so which means that yeah. So as I just explained, maybe let me just explain a little bit. So if you you have this map, so you have a map from M double star, and suppose that this is reflexive in codimension 1. Suppose phi p is an isomorphism for height p equals to 1. Then suppose that it's not an isomorphism globally, then you can choose. If phi cell is not an isomorphism, choose a prime, a minimal prime, that it fails. Then you localize, you will get, maybe let me call this Q. So now you localize and you localize and you have a map between MQ and MQ double star, and you have the kernel and co-kernel. You have K and C equal to co-kernel. And because you choose, I want Q. Because you choose Q to be minimal, we know that K and C have finite length. But now the condition that depth of MQs is at least 2, because we know that everything works in codimension 1. That leads to a contradiction, right? So you cannot have a map from a depth 2 module that has kernel and co-kernel finite length. And so that if it's reflexive in codimension 1, then it's reflexive, then the module itself is reflexive. So let's get back to the talk. So the case of dimension at most 1 is really crucial in understand reflexive module. So it is very cool. I cannot hear anything. Are there any problem with the audio?
No problem as of now.
Okay. So let's try to understand what happened in small dimension, namely dimension 0 and dimension 1. So the warm-up result, which is classical, is that if in the 0-dimensional case, the following are equivalent. So we have an Artin local ring, and the following 4 statements are equivalent. So K is reflexive. The omega R, which is the canonical module, always denote the canonical module, is reflexive. Every module is reflexive, and R is Gorenstein. So this in the Artin case, these are equivalent. So maybe let me go back to the proof case and just sketch some proof. So of course, if let's see what happens if K is reflexive. So if K is reflexive, so when you look at, so we're just going to compute K star. So this is equal to harm KR. Of course, is equal to the circle of R, which is K to the type of R. And so K, because of that, K star star is equal to K to the type of R square. And if this equal to K, if it's isomorphic to K by reflexivity, then it forces the type of R to be 1. right? Which is Gorenstein, the Gorenstein condition. But if R is Gorenstein, how can we show that every module is reflexive? Well, you can do it in a number of ways, but the most elementary way is probably induction. We show that every module is any M reflexive, sorry, reflexive by induction on length. All right, and well, the case length of M equal to 1, then it just means that M is the residual field. And that is handled above. And then you can, for length of M bigger than 1, then you can fit N into take a filtration and fit N into a Schrödinger sequence with something of smaller length on the left and K on the right. And then you dualize. And here I have to use the fact that I have vanishing of X. So I'm going to, I can take the double dual of this sequence, and it still give me a Schrödinger exact sequence. So any proof that you use would have to use the fact that the X functor against R is equal to 0. So if you analyze the proof carefully, you will see that it's always the case. And then the snake lemma will, and induction will finish off the the proof. Okay, so we have the two, the left and right map are isomorphism, and so the middle one also. Okay. Right. So so this for, and you can use the proof for that omega R is reflexive, means that R is Gorenstein. Maybe let me make a comment. So if omega R is reflexive, then I take a shock is a sequence like this. So I take a projective cover omega R dual, and then I dualize this thing. Then I get omega R goes to F check, go to X check, go to 0. Here check mean harm against omega. And because of and this Schrödinger sequence has to split. Oh, sorry, I sorry, yeah, I mean so I made slight mistake here. We don't know that X vanished against R, but we still have co-kernel, so something like this. right? And then sorry, so and now because x1 y omega is equal to 0, so this split. And that implies that omega r is free. And that force R to be Gorenstein. Okay, so so this warm-up theorem holds, and the crucial point really, though, that you have to use X vanishing in showing that everything is reflexive. You need the X vanishing against R, which is characterized by Gorenstein property. So the question is, what happened when R is not Gorenstein? And it's a very interesting question. By the way, it's considered recently even for non-commutative Artin algebra. Maybe let me make a comment here for people who are interested in. Ringo in very recent preprint shows that that if R is an Artin algebra, so A is an Artin algebra, not commutative. So if you only assume that all simple or reflexive, does not imply that that A is self-injective. So in the commutative case, of course, for an Artin algebra, if all simples are reflexive, then the ring itself is Gorenstein, self-injective. But in the non-commutative case, it doesn't hold. In fact, such a question, very natural question, was only considered recently. I just tell us that there's still again many interesting things that are unknown. But back to commutative case, when R is not Gorenstein, we know very little about reflexive module, and I think that's a rather interesting topic. And there are some partial results, but I'm going to skip that this situation. So I'm going to focus today on the case of dimension 1, local Cohen-Macaulay ring, and assume that R has a canonical module. Now, this situation appear a lot, and usually I will assume that things are Gorenstein on the generically, so that this situation appear already a lot in commutative algebra and algebraic geometry. And in this dimension 1 case, we also have a familiar result. So the following 3 statements are equivalent. Omega R is reflexive. The reflexive module are precisely the maximal Cohen-Macaulay module. So it just this is all depth M equal to dimension of R equal to, well, 1 in this case. So all Maximo Cohen-Macaulay are reflexive, and R is Gorenstein. So of course, in dimension 0, all modules are Maximo Cohen-Macaulay. So this is a natural extension of the warm-up theorem. This is also, and you can prove it in similar way into the Artin case, it's a pleasant exercise to do if you haven't seen it before. And we will in this talk generalize this theorem later, right? So I will remind you of that when we get back to the when you get to the main results. But yeah, so very similar statement to the Artin case. And in fact, you can, as I say, because understand reflexivity is really boils down to dimension 1, at most 1. So this statement can also be extended to high dimension, but we already focus only in dimension 1 today. So okay, so from now on, I will make some technical assumption. So I mean, many statements that we found hold true in rather general context, but they are most efficient and most elegant to state when you make some assumption. So first, I will assume that R is already complete, and then I will assume that is generically Gorenstein. So all minimal primes localization are Gorenstein, and that, you know, because as I mentioned earlier, if you want your module to be reflexive, it better be reflexive at the minimal primes. And the case of non-Gorenstein Artinian base ring is already quite complicated. So we'll assume generically Gorenstein. But this is from the point of view of many situations, is my assumption. For example, you can take any complete local domain, or take any even reduced complete local ring. And so the typical example that I have in mind is, so this is where we see this curve singularities, right? So for example, you can take a numerical semi-groups, 3, 4, 5, and ask what are the reflexive modules over this ring. Or you can take Stanley Richner ring, KXYZ over XYYZ ZX. Or if you like to think about it in a slightly different ways, this example is, coordinate ring of 3 points in projective space. So they are all, so coordinate ring of points in projective space are all reduced. And you can also ask, well, what are the reflexive modules over this ring? So to talk about what comes next, I need to a couple of familiar notations. So QR will denote the total quotient rings. So just a localization at all non-zero divisors in this case. And R bar would denote the integral closure of R inside QR, right? So we look at all elements, all fractions in QR that satisfy polynomial equations with coefficients in R. Okay, so this again very basic and fundamental notations. Okay, so our goal is to understand the reflexive module, but let me try to pose the questions more concretely. So, for example, we can ask what module. Can we give us some concrete example when a module are reflexive? And how big can the reflexive modules be, right? Are there infinitely many indecomposable reflexive modules? And then if you want to study the sort of the algebra or geometry of it, then we should ask how the size or the structure of reflexive modules reflect the singularities of R, right? And that so the third question has been, well, all of this question has been studied for the category of Cohen-Macaulay module under the name Cohen-Macaulay representation theory, right? So the idea is to use the category of Cohen-Macaulay modules to understand the singularities of a local ring, and that has been a very successful and active area. Are there any questions so far?
So far, there has not been any questions written in the chat box.
Great.
If someone has a question, one can ask, unmute and ask now.
Yeah, and please let me know if I'm going.
Yeah, if I see something, I'll immediately pass it on to you.
Okay. Yeah, and you feel free to ask question, please, because it's feel a little strange. Just talking
I understand.
without any feedback. And also if I'm talking too fast or the handwriting is hard to see, please let me know. Anyway, so so these questions are fairly natural, and but still, if R is not Gorenstein, it's not obvious what the answers should be. So let me make a comment about these categories and how this reflects the singularities. So we have the free modules which sit inside the reflexive module, which in turn sit inside the, again, I'm still in dimension 1, right, for the rest of the talk. And the reflexive module sit inside Cohen-Macaulay module, right? So all reflexive have depth 1. And so they are nested in this way. And it's a classical theorem that if all Cohen-Macaulay modules are free, then that's equivalent to R being regular, right? So, or smooth if you like to work over geometric setting, over algebraically closed field and K-algebra. But what I just explained in a few minutes ago also tell us that if the reflexive module, the category of reflexive module is equal to Cohen-Macaulay, maximal Cohen-Macaulay, then it's equivalent to R being Gorenstein, right? So therefore, it makes sense to speculate that the sort of relative size of ref R should contain important information about the singularity of R. And in fact, that sort of the main one of the main motivations for our project. Well, the other motivation is just, well, it seems annoying that we don't understand reflexive modules that well when we want to fill that gap. Okay, so let's get to the first question. What modules are reflexive in the non-Gorenstein case? Well, it turns out that M, the maximal ideal, is always reflexive. This is actually not an easy, well, it's not super hard, but I will ask you in your free time to try to prove it. From scratch is not an easy exercise to, and so, but I mean, it can be done, but and M is actually always reflexive. And also, R bar, which is the integral closure of of R is reflexive if it's a finally generated module. Okay, for example, if R is reduced, and again, let me remind you that we are in the complete local case. So then R bar is, if it's reduced, and R bar is a finite module, and R bar is reflexive in that case. So it does seems like
Hi, Long.
so yes.
So there is this question: if all these are specifically for dimension 1.
Yes. So for example, if dimension is, well, okay, R bar is still reflexive in dimension higher. If you assume under certain assumption, because remember we have yeah, okay. So let's go back to the remark here, right? So remember, we know that to check reflexivity, you need to check reflexivity at high 1, and also we need to check depth at least 2, right? So there are 2 sort of condition. So R bar, as long as is reflexive in codimension 1 is reflexive. Now for the maximal ideal, then it will fail with the S2 condition, because the depth of the maximal ideal is always 1 in higher dimension, right? And so, oh, I'm sorry, I mean, yeah, assuming S2. So so in higher dimension, M will fail to be reflexive, but R bar still is. Okay.
Yeah.
Did that answer the question?
I assume so.
Yeah. And yeah, so great. So so there are, well, 2 simple but important objects, right? In mod R are reflexive, which is a good news, I think. It tells you that this thing are interesting. But do we know more? Right. So we know that free module R. We know that the maximal ideals are, of course, the direct sum of 2 reflexive module reflexive. So direct sum man of all this reflexive, but still not too many. And so we have another observation by in a paper by Corso, Hunicky, Gas, and Vasconcelos, and it's say essentially that if R bar is finite, then all integrally closed ideal are reflexive. So that's good, but we still, you know, in for example, if you look at the complete local domain, then there are only finally many integrally closed ideal, because, you know, when you extend to R bar, it become a principal ideal, so it only depends on the order of that, right? So maybe let me just say, make a comment here. So let's say that is complete local domain, dimension 1. And so if I is integrally closed, just saying that I bar intersect R is equal to I, right? And but I bar is really the ideal of T to the order of I. So it only depends on the order, right? So R bar, I guess R bar is really KT here in this case. And so this ideals on so I bar only depends on the order, right? And there are only finally many order up to the conductor that you can take before it become isomorphic. So they all, up to isomorphism, they're only finally many intervally closed ideal. So, right. So we still, in the non-Goranskian case, have only finally many examples of reflexive modules. So let us try to extend the proposition by Koso, Huniki, Kass, and Vasconcelos a little bit. And so here is a extension that allow us to give a new subcategory of reflexive modules. And so let S be a finite birational extension of R, such that, and this is condition that we will see that we'll completely understand later. But let me just say that yes, so we want that all Cohen-Macaulay module over S to be reflexive over R. Of course, that include X itself. Then, and this only satisfied when S is the integral closure. Then you take any contracted ideal, right, and it become reflexive. So that give in a way an extension of the observation by this four author. And it also give you a way to generate more reflexive ideals. We will see more example of this, but so let me give a quick proof of this, right? So so S is a birational extension. Birational extension of R, and we assume that all Cohen-Macaulay module over S are reflexive over R. So I want to show that, so let I in R, right, and the J equal to the contracted, so to I expanded to S and then contracted back to R. So I have J double dual with respect to R is inside IS double dual. But remember, IS is in is a Cohen-Macaulay module over. Okay, I should say that has to be a regular ideal. I should say. Let me go back and so I here have to be a regular ideal. So I need to assume that in the dimension. So I contain a non-zero divisor. So I. Or have height 1. Okay, so height I equal to 1. Okay, let me just write here. Height I equal to 1. I forgot that. Okay, so then IS is a Cohen-Macaulay module over S, and so it is reflexive, right? And so is equal to IS, and so that means that J double star star is inside IS, right? So equality happened. Double star equals J. Okay. So that's a simple, but the key point, however, is to understand when this condition is satisfied. And so that brings me to the first main theorems. So again, S is a finite birational extension of R. And the question is when all Cohen-Macaulay module over S are reflexive R module. And you can see it as, view it as sort of a strongly reflexive condition for S. So first theorem, again, you can state it in slightly more general situation, but suppose that R is complete, generically Gorenstein, still dimension 1 and Cohen-Macaulay, of course, and the residual field is infinite. Then the following condition are equivalent. And before you stare at this condition, I want to remind you that we have a very way earlier, we have the classical theorem that if omega is reflexive, then it's equivalent to every Cohen-Macaulay module reflexive, and R is Gorenstein. So this theorem can be viewed as an extension of that theorem, but for birational extension, not just for R, right? And so, so the first two condition is familiar. So all Cohen-Macaulay module over S are reflexive, and we only need the canonical module of S to be reflexive. And the third condition to replace the condition that R is Gorenstein is a little bit more technical. So it turns out that you need the conductor of S. So the conductor is equal to all the alpha in QR that multiply S back to R. And so the conductor of S has to be inside the core of the canonical ideal, of some canonical ideal, colon that canonical ideal. So the core of an ideal is the intersection of all X when X is a minimal reduction of that ideal. So in this particular case, omega R. Okay. X is a minimal reduction of omega R. So when when R is Gorenstein, of course, this then omega R is any ideal you choose, it's just a principal ideal. And so any minimal reduction is itself. And so this colon would just be R. And so this say that the conductor always lie inside R, which of course always satisfy, and then that just the Gorenstein condition for R. But is this theorem say that to have this strong reflexivity condition, so all S module are reflexive, or Cohen-Macaulay S module are reflexive, you only need to check that the conductor lies inside a fixed, some fixed ideal. And then this, on the right-hand side, the ideal does not depend on the copy of canonical ideal that you choose. Okay. So that's our first theorem. And that gives you many. So if you choose your ring, so that, for example, if you choose your ring so that there exists S of infinite Cohen-Macaulay type, so there are infinitely many Cohen-Macaulay S module up to isomorphism, then you get infinitely many reflexive module over R. So I believe this is the first results that give a general way to demonstrate that you may have infinitely many reflexive modules. And let me describe the second theorem. I'm running out of time. That sort of fit into the theme of if R has nice singularity, then it has small reflexive module category. So to describe the singularity, I need to look at the conductor of the integral closure. And the theorem say that if the co-length of the conductor is small, so it's almost 3 or is 4 and R is Borenstein, then the set of birational extensions that are reflexive are actually finite. So they're only finitely many. And in fact, it is one-to-one corresponding to the set of regular ideals that is a trace ideal and reflexive. So this set is finite as well. And this is actually a sharp. So this condition is sharp. So you can give a non-Gorenstein ring with conductor co-length equal to 4, such as this is the conclusion does not hold. And I think I'm running out of time. I just put here one quick example, so where you can get all finally many reflexive, indecomposable reflexive module. So K, sorry, mod XY, mod YZ, mod XZ, and then R itself. Because I raised a question about these two particular rings early on, and so for those two we can completely write down the set of indecomposable reflexive modules. But anyway, I should stop here.
Yeah.
Yeah, we can take questions from audience.
Like how much of this goes into dimension? If you take dimension 2, I mean, it completely changes the scenario, or like?
Oh,
you have,
again, you higher dimension reduced to dimension 1, right? Again, back to the point that I explained very early on. Very, it's the second page.
Yeah.
So, right. So, so to check that something is reflexive, and suppose that you already know that it's Cohen-Macaulay, for example, right?
Yeah.
Or S2, or you only need S2. Then you only need to check that it's reflexive on the height one.
Yeah.
Right. So, for example, as I said earlier, if the integral closure is still reflexive, if it's under my condition, so that is finite, right? So
Yeah.
So it's all reduced to dimension 1, which is why we want to understand dimension 1.
Okay, thank you.
So we'll